Swayam Prabha, free DTH channel for education.
Given that we have already discussed these things in the last Zoom class as well as the last couple of videos, I'll go more like a summary mode, but feel free to stop me at any point of time. Okay. So first thing we discussed is in case of CT images, you will be having an object, but what you could see from your process is assume that a 2D object is there for the sake of simplicity. All you could see is in case the projections of it is what you could in fact measure, right? Whichever is there. So assume that this is your detector on this given function of f of xy, okay, where this is x and y, and let's call this as x dash here. So what you would be, so if you want to just put me here, okay, suppose this is making this sensor is making at an angle theta. Now what you are in fact measuring is where, for example, one thing you would be looking at is in case of x-rays, it's the absorption coefficient by various tissues, structures, whichever are there in the in the head. So let's say if the head CT image is taken, so you will be an integration of, so X-ray is coming like this. So things, there are different objects in between. Okay, this is a 3D f of xy. So we assume that it is projected something into the space here outside your screen. Okay, so this gets absorbed, and all that you could measure is, let's say in case of CT, you would be measuring the absorption coefficient across this line, right? So that's how you do it. So suppose if you want to put as the coordinate axis, for example, now if you somehow move it to, let's say this x dash, I'm keeping this as a coordinate here and this as y dash. So let's call this function as g theta, because this would vary with varying theta. And now you have x dash here, let's call it as g theta of x dash. That's what we started with. Then the first thing we discussed there is how do you write g theta of x dash expression. So now if you move to, for example, f of xy, if you could represent in terms of x dash and y dash, then you have this information in terms of some other function. Let's call it as g of some x dash comma, or g is overlapping with this. So let me call for the time being h of x dash comma y dash. You write into some other function. Then how could you get g theta of x dash? Then you have, let's say, to get this, what you should do along y dash axis, you will integrate all absorption coefficients there. So y dash of minus infinity to plus infinity. This f of xy, you are going to write equivalent function. Let's call it as h of x dash comma y dash and dy dash. So that's how for a given x dash, you will be getting this value, right? By the way, this 0 here is also same as the 0 here, right? For this x dash, that's how you would take here. And then what we did is, how could you get h of x dash comma y dash? So for that, we have looked at rotation of coordinates axis. So if you have x and y here, and now you rotated them, let's say in the anti-clockwise direction by an angle theta, and assume that you have here, yeah, x dash, y dash. Then what did we get here? X equal to x dash cos theta. Then what? Any idea for any point x comma y you take x dash cos theta? Minus or plus? Minus y dash sin theta. Okay, and y equal to x dash sin theta. This we have derived it in the last class. Okay, plus y dash cos theta. We will, for the sake of the future kind of work that we would be doing, let me write it in the matrix form also here. So this would be equal to cos theta minus sin theta, cos theta of x dash y dash. Let's call this by name capital X. This let me call it as a subscript theta. Okay, and this let me call it as x dash. Okay, this is what I had. Now we also derived now values for x dash from this. That turned out to be x dash equal to a of minus theta times x, right? This is what the expression we got. How did we get that? You just multiply both sides with the inverse, and a theta inverse would become a minus theta. That's what we got. So if you want me to write now in the full form, it could be x dash equal to x cos theta plus y sin theta. Just replace here theta with minus theta. Y dash equal to minus x sin theta plus y cos theta, right? And we use this to write now f of xy. That implies your f of xy will be, how could you write that? You just replace that with these values, right? And what would that give us now? G theta of x dash, let me directly write that expression for that, because we have written it n number of times already. So g theta of x dash is y dash varying from minus infinity to plus infinity f of, okay. So this xy, let me write it as, first you will see this notation would be convenient as I move on later. A theta times x dash y dash. This is how I am writing it. Okay, just this is basically this expression xy. A theta times this only. I am just putting x dash y dash into dy dash. What is this known as?
Redound transform.
Right, a very important transform. Found sometime around 1917 by a person by name Radon. Later, this turned out to be a very important relationship for CT and all these projections. Okay, this is the equation giving you the projection details, right? What did we do after that? What we have done there is to establish the relationships now in the Fourier domain. That's what we tried doing that. So now you have an object here, x and y. Let's call it as f of x comma y. You take the two-dimensional CTFT of it. Let's call it as f of kx comma ky. Okay, you have something here. Now you take a projection of it now, just like we did earlier. You'll have you have a projection here. You are taking that on this detector. Okay, this projection. So this, for example, let me keep this here. So this is at an angle theta. So this we are referring it. This we are calling it as x dash here, and you are getting some profile for it for varying values of x dash. So by the way, 0 would match. That's important thing. Okay, so we are calling it as g theta of x dash. And now for this, you compute the one-dimensional CTFT of it. So if you are computing the one-dimensional CTFT, let's call it as capital G theta of, anyway, this variable is different. So let's call it as with some other name, not to confuse with this kxky, because that's exactly in this direction we are going to compute. So let's call it with another name, G theta of rho. Let's say I have the profile of it here. This is for varying rho. Okay. And for a given theta, this is what G theta of rho is. How is this related to f of kx ky? What was the relation we arrived at the end? So we started with the simple projection parallel to the y-axis, right? And what did that correspond to? Projection, if I am projecting the x-rays parallel to the y-axis, okay, and computing the Fourier transform, what does that Fourier transform correspond to? In other words, my theta is 0 here, then I got an x prime there, okay, and for this I have taken a CTFT of it, okay. Let's call it as z0 of rho. What does that equal to? for varying rho. What did I get there? In terms of f of kx, ky? This would correspond to, hope you all remember that. This would correspond to along the kx axis we got, is it not? So this would give you along this axis. So that means that is equal to f of, how do you write it? You tell me this expression now. Just imagine a parallel projection here across the y-axis. So rho and kx, how do they correspond if I give there? Are they not same? If I am taking a parallel projection here, so I maybe I'll quickly draw it. So I'm taking a parallel projection here. Okay, then I am getting this. So what would happen now when I am taking it? This would be 0. This is my x is same, right? This x. So basically that and rho would correspond now. So this would be equal to rho comma 0. Is this clear?
Yes.
Good. So then I would, if you had followed it, I will extend it now. Now you tell me g theta of x prime. Okay, I have it. And further, the CTFT of it is g theta of rho. Now you tell me what is this equivalent to? If it is at an angle theta, this we have derived already in the last class with an intuitive proof. This is what it would correspond to. This line would correspond to this line, but remember that this would be rotated across this 0. If it is 0, you just need to rotate it by theta here, and that would give you this, right? This would be your g theta of rho here. Okay, now you tell me, what should I write here? F of
kx dash comma 0.
Rho cos theta comma 0.
Now is ky 0 here for this
Rho,
point?
rho
No,
sin
no.
theta.
Rho sin
Very
theta.
good, very good, very good, excellent. That's right. So now what happened? You had it here, for example, any point you take now here, okay, across this. For a given row, now this is your row value basically here. This is your row. So x value would be equal to rho cos theta, and y value would be equal to rho sin theta, because this is equal to theta. This is, yeah, in my, even in my last video presentation, this final expression I have not explicitly written, although we discussed the concept there. So this is the important Fourier slice theorem now. F of rho cos theta comma rho sin theta. That was Radan transform earlier. This is called as Fourier slice theorem. What were the other names? Projection slice theorem, and another central cross section theorem. Clear? Okay. There, the way we derived the proof is more of an intuitive nature rather than a rigorous proof. What we did, the way we proved this relationship, that if it is there on a sensor at an angle theta, that will be corresponding to theta. The way we did is we took for parallel projection there across parallel to the y-axis, and that corresponded to ky equal to 0. And after that, what we said is, if you are rotating the object, then this Fourier transform also gets rotated. So that way you could say rotation of projection taking at a different angle is also equivalent to taking parallel projection, but now rotating the object in the opposite direction. That's how we proved. But I think it would be good to flex your math muscles here by doing a rigorous proof as well. Just follow with me again, work it out in your notebooks. This would help you. If this gets clear to you, most of the things would become quite comfortable to you. Okay, so what we need to do in the proof, that you first think about it. I need to write expression for f of kx comma ky on one side, and I should have expression for the Fourier transform of g theta of x prime. which I am calling it as g theta of rho. Okay, so and then I need to see a relationship between these two. First, let's start with what we are very comfortable. F of kx comma ky. You tell me the expression in terms of f of xy. You should be jumping on this by this time. Minus infinity to plus infinity, minus infinity to plus infinity, f of x comma y, e power minus j 2 pi kx into x plus ky into y dx dy. Okay, right. Now let us try to write the expression for this part. Okay, now we already have the expression for g theta of x is already there. What was the expression? G theta of x prime we have. Okay, we should be very careful with the not mess up with x and x prime. Okay, so what was the expression for g theta of x prime? That's equal to y dash varying from minus in, please work out along with me in your notebooks as I mentioned, y dash varying from minus infinity to plus infinity. So this is the expression f of a theta times, okay, this I think this is multiplied with x prime y prime, x prime y prime, right, into dy dash. I'm just rewriting the expression which we have done here. Okay, now let's write, how do you write the expression now for the Fourier transform of it? G theta of rho is equal to, let's say I want to write it in terms of g theta of x prime. What is the variable here for me that I need to vary?
X prime.
Right, x prime varying from minus infinity to plus infinity into what should I get here?
E power minus j 2 pi x dash.
Good. E power minus j 2 pi.
Sorry. Kx dash x
No,
prime.
sir. No, 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 no. We are not in kx space now.
Rho X prime.
This is rho now. Okay.
Rho x prime. Yes,
Rho x prime. Correct?
Yes, sir.
Yeah. So let me now substitute x prime there. Okay. Minus infinity to plus infinity. And then this is nothing but, again, I have g theta of x prime is y prime varying from minus infinity to plus infinity, f of a theta into x prime y prime. I'm writing it this way. Okay, into, so that d y prime. Okay, I'm just simply substituting here. I'm going slowly, so I'm just still keeping that also inside. 2 pi rho x prime into dx prime. Okay, so let me now take that out. So my x prime is varying from minus infinity to plus infinity. Y prime is varying from minus infinity to plus infinity. F of a theta of x prime y prime, right, into e power minus j times 2 pi rho x dash into dy dash or dy prime, whatever you call it. Okay, this is what. Then what do you think we should do now, such that g theta of rho, somehow we have to express it in terms of this way, right? What should we do now? What kind of thing we should be doing now? How can you achieve that? This is your fk kx ky. Okay, somehow you want to compare that with g theta of rho. What should we do?
So what's the question again?
See, this I need to write. See, finally, g theta of rho, I want to express it in terms of f of kx comma ky. So this f of kx comma ky expression format, it has to come finally, right? So what do you think we should do now for getting into that form? So instead of x prime y prime, okay, you take them. Can you express it in terms of x and y? See, these x and y exactly make sense here. So do we have any expression for that? X prime y prime is equal to, what is the expression here? Right? A minus theta into x prime y prime is equal to a minus theta into x comma y. So replace or let, whatever you call it. Okay, so this change of axis, or in other words, change of these variables is what you are going to do. Then what would happen inside this function now if I'm doing that? Then f of a theta into x prime y prime, what will happen to that value?
F of xy
X
it
comma
will be
y.
coming.
Right, good. That's how we are getting f of xy here. Right. And now x prime is, anyway, once you are doing it, what does that mean? A minus theta is in fact, can you quickly tell me? Cos theta. Please refer your notebooks, and if I am writing something wrong, alert me. I think this is the expression, right? So x prime is equal to, you multiply that matrix with xy, so that would give you x cos theta plus y sin theta. So that you could do here, right? You are able to get rid of this. Anyway, now these two would still, even if you are rotating it, still it will be minus infinity to plus infinity. There is no limits issue is there, but how do you resolve this? Dx dash dy dash. Okay, that you should now write it in terms of dx dy. Any idea on how you could do that?
Differentiate the equation.
Yeah, there are two variables here, so Jacobian would come into picture. Okay, so from your calculus, I hope you are aware of this. Let's say dou x dash by dou x dash by dou y, and then you do it now. On one side you have x dash and y dash. So do now for y dash you take with respect to x now, dou y dash by dou y. You take this determinant, multiply it with dx dy, that would give you dx dash dy dash. This change of variables, you should have studied it in calculus. Okay, when there are two dependent variables, because see now how things are there. X dash equal to x cos theta plus y sin theta, and y dash equal to minus x sin theta plus y cos theta. Now we want expression for dx dash dy dash in terms of dx and dy. So when that kind of thing is there, Jacobian, okay, where you are taking derivatives with respect to x and y, okay, then you multiply with dx dy, that would give you dx dash dy dash. Okay, hope some of you at least remember this from your calculus, where you are doing change of two variables, you are changing it. Okay, now what is this determinant here? Can you tell me this, the value of this determinant?
1, sir.
Right. This determinant value is 1. You just simply check here, apply it. You will see that determinant cos square theta plus sin square theta you'll be getting. So that implies your dx dy is equal to dx prime dy prime. Very comfortable. Okay. If you want, you go back to x equal to r cos theta, y equal to r sin theta. In our earlier classes we have done. There I was giving you an intuitive geometrical proof for saying that dx dy equal to r dr d theta. Exactly, you could apply there also this Jacobian, that would give you mathematically rather than geometrically. Okay, anyway, coming back here, now you substitute them there. What do you get now? G theta of rho is equal to, now your x and y are varying from minus infinity to plus infinity. Inside this, now this turned out to be f of xy, right? And then what? E power minus j 2 pi rho x dash. In place of x dash, what should we write?
X cos theta plus y sin.
Right, x cos theta plus y sin theta. What else? Is there anything else? That's all. Dy dash dx. Then that will become now dx dy. Okay. Now compare it with f of kx comma ky now. Okay. What was f of kx comma ky? Minus infinity to plus infinity, f of xy into e power minus j 2 pi kx into x. I'm just rewriting the expression because it is too far on the top. So I'm just writing it here. Hopefully not committing any new mistakes. Dx dy. So from that, now what could you say here? G theta of rho is equal to f of what? You could substitute values of kx and ky, right?
Rho cos theta, rho sin theta.
That's it. Notice here, if I put here rho cos theta, this term is 2 pi rho cos theta into x. If I put here rho sin theta, 2 pi rho sin theta into y. This is a more rigorous mathematical proof rather than making use of the rotational property there. Okay, that's the Fourier slice theorem. The same thing, but now we did more rigorously. Yeah, with that, this part is done. Those of you who had again seen the presentation there, I was discussing there what would happen in this case. Now you have all these values at along the radial directions. Now you have it. So that's equivalent to having along these lines, but you want it on a regular grid here. So you could see here, if you want to interpolate a value which is close to the origin, like let's say within the circle that I have drawn, there are a lot of other known values surrounding it. So interpolating it using cubic interpolation or whatever you want to use, or a spline based implementation, is up to you. You could do it more accurately, but you could notice here, as you are going far away, the number of points surrounding that you have is reducing. So in practice, you won't right away would be using this Fourier slice theorem to compute, to reconstruct the 3D image. But what you would rather do is something based on these concepts without exactly going into the Fourier domain. That's what you would be attempting at. Okay. So again, there are some algebraic methods also on the other hand. Again, I'm just giving a just a pointer to what we would be doing later. Okay. See, for example, here, what you would do is in case you could start there in kx ky acquisition itself, you will go like this, and then you increase your y value, then you keep changing these x values like this, then further increase by one step, and then in steps you increase it. So that's how you would be doing in case of MR imaging, direct acquisition in kx ky space. That's the beauty of it. Okay, so there is no problem of interpolation that we got in the CT case. So there it is pretty common. If you notice, even the one of the books that I shared, particularly the Nishimura textbook, there what they would be doing is they would be in fact stopping at Fourier slice theorem only, because that's good enough for MR imaging, as you will be acquiring your samples in the KXKY space. And while acquiring, you have the flexibility to get it on a uniform grid. And of course, there will be other ways also to fill this uniform grid. For example, one could go diagonally, then come, and they will see what would speed up things. But just it is enough to note at this point that Fourier slice theorem serves as a basis for more advanced methods in CT, although it might not be many times used. But on the contrary, there are a lot of MR acquisition techniques where they would be acquiring the signal in KXKY space on the regular grid. So in that case, Fourier slice theorem is good enough there. They do the reconstruction with simply Fourier slice theorem. Unless they are also taking samples in a different way, then they would borrow or adapt methods from other coming from CT image reconstruction. Yeah, initially CT is there for quite long. In 1900s it is there, but 1980s, I think, around that time, or yeah, around 1980s, I think the MR has come. So lot of methods are inspired from CT only. The acquisition, how you do it, Fourier slice theorem, these projections, all these methods are adapted initially from CT imaging itself. Okay, so any other questions? Everybody fine with that? Then I'll stop the recording part.